All right, so we're back with Chapter 5, now Part 2, and we're continuing with thunderstorms. So now we talk about multi-cell thunderstorms. And these are the severe thunderstorms, the ones that cause damage. Often will have tornadoes as well. And these are some of the strongest storms that we see in the Midwest. So they consider it a severe thunderstorm if it makes hail, that's one of the signs, a tornado, or you've got wind gusts of almost 60 miles an hour. So pretty strong actions. And one of the things that happens in a multi-cell thunderstorm, they call them a supercell sometimes, is it has a specific rotation within the clouds. And this rotation, called cylindrical updraft, leads to tornadoes. Okay? So it's very, very, very rare that a tornado does not form in a supercell. It can form in the single cell once in a great while, but mostly in these. And you need this to form over land. You have to have very humid air and very strong wind shear. And here's what happens. So here we have wind shear. The wind up above, so maybe 10,000 feet up, is blowing much, much faster than the wind on the surface. And so what happens is it basically starts to cause the wind to kind of roll. So instead of blowing just this way, it kind of rolls it. So you have this kind of rotation, right? A rolling cylinder, almost like a wheel. When this happens and it encounters warm air that is rising, just like before, it takes that cylinder and it basically lifts it upright, right? So the cylinder hits this warm air and is pushed. And this rotation now becomes vertical. And that creates a mesocyclone, a vertical rotation in the pattern. This looks like a tornado. This does not mean it's automatically a tornado, but it can lead to it. But what it does do is this rotation helps drive the warm, moist air even faster, even further, higher. And sometimes these clouds will reach the top of the stratosphere, right here, and they form what's called an anvil. It just goes so high, and it takes so much energy in the form of moisture and heat to do that, that it forms a lot of energy. And what happens is these whole clouds rotate. They look kind of like this. This whole cloud, if I had a little movie, would actually be slowly rotating. Now, the reason it's not a tornado is it doesn't touch the ground, but it can lead to that, and we'll get to that. So two of the most devastating aspects of thunderstorms are lightning and tornadoes. Lightning, just in case you don't know, it's electricity. It's basically static electricity. So the same thing you get when you go to touch a light switch, or maybe you grab something that's metal, you get a little zap. It's just on a scale millions of times larger. And lightning occurs in many ways, cloud from one point in a cloud to the next, or from cloud to ground. Cloud to cloud is the most common, by the way. And like all electricity, lightning follows the path of least resistance. Different types of material allow electricity to travel better. So that's why things that don't allow electricity to form, to travel well, like rubber or plastic, we use that to wrap wires. Otherwise, if you touch the bare wire, metal, we as humans are very good conductors. So is anything that's wet or living. And so tree roots, wet soil, lightning will follow those first because it travels fastest. It's interesting. I got a picture of this. If lightning strikes a beach, especially if it's wet sand, right? It's so hot. Electricity, the lightning bolt, is hotter than the surface of the sun. It lasts only a few seconds, but it is so hot that when it encounters sand, it turns the sand into glass. It forms what's called a fulgurite, and I'll show you a picture in a little bit. Now, we see lightning instantaneously, and we also hear the thunder. Thunder is actually a shock wave, right? What happens is lightning is so hot as it passes through the air at the speed of light, it heats the air around it to the point where the air explodes and forms a shock wave. So lightning is what we see. Thunder is the lightning igniting the air next to it. It's that fast. We can actually see here a couple different types of lightning. Here we see cloud to cloud, going from here to here, within the cloud. And then we see here cloud to ground. And this is a fulgurite. This was dug up from a beach. So lightning hit the beach right here, and it traveled through the sand, eventually dissipated. It turned all the sand, it melted it into glass. So what happens? What causes it? It's basically electrical charges. There's all these different ions and molecules in the air. And if you remember from basic physics or basic science, right, atoms have electrical charges, usually neutral, right? You have enough positive and enough negative things in the atom to be neutral. But in all the turbulence of a thunderstorm, the wind moving, all these atoms and molecules bump against each other, and they're like tumbling all around, and they might lose an electron or a proton, and now they might have a positive or a negative charge, right? Especially oxygen does it all the time. It'll lose an electron here and there. So now you have negative and positive. And remember that negatives and positives like to stick together like magnets. And so what happens is things tend to basically get separated. These charges build up, different charges, negatives and positives, and they kind of gather together like magnets. But what happens is they want to even out. If it's positive or negative, it wants to be neutral. And if you put positive and negatives, enough of them far apart, they will basically bridge that gap to even out. It's like when you have two magnets and you put them together, they kind of snap. Same thing. But we see that as lightning. Okay? So here's an example. Here you have this cloud right here, and all this mixing is basically creating millions of positive and negative ions. The positive ones tend to accumulate up here, the negative ones here. And when there gets to be enough that there's a big gap, it'll basically even out. And that's what the lightning is. It's evening that charge. Now, when we see ground to negative, that's because the Earth has a generally positive charge. Just enough that if the negative ones build here enough, you see that ground to Earth. And that's all that is. You do the same thing. If you've ever walked across a floor, like a carpet, and you're wearing socks, and you drag your feet on the socks, that dragging creates all this, and then you have a buildup of positive or negative charges within your body. And if you touch something that's positive, like a light switch, you get that little static electricity shock. I know I used to go to my cousin, and I'd touch her in the back, and she would jump. So I've always thought I should cut this part out of the lecture, how to stay safe at lightning. I find it interesting that in a college class I have to give you a safety lecture, but there are some things you should know, which kind of also talk about this, that lightning and thunder do not happen simultaneously, because light travels faster than sound. We see the lightning, then we hear the thunder. Now, you can actually use that to calculate the distance. If you see lightning and you see the thunder, you hear the thunder 5 seconds later, I'm not going to make you do the math, but basically this is that the longer the time between when you see it and when you hear it, the farther away it is. Sometimes in a great while, you'll have a bright flash, and it sounds like a lightning explodes right in front of you. It's happening real close. Makes you jump out of your skin. It's right next to you. But what they say is this. If you're outdoors and there's 30 seconds or less than 30 seconds between lightning and thunder, then you need to be careful. Okay? And you need to wait. Now, here is the things. These are things that you should not do in a thunderstorm. So first, please, no mountain climbing in a thunderstorm. In other words, don't go to the highest place because you become the closest part, right? The higher you are, the closer you are to the cloud. If a bolt of lightning goes from cloud to ground and you're the closest thing, you're also the path of least resistance. Just like you don't go golfing. Because what you do when you golf, you have a big metal club in your hand, big golf club, right? You stick that up in the sky and there's like a big metal lightning rod. Do not stand under a solitary tree. And that's not because the tree's going to shock you, but what will happen is if lightning hits that tree, which it will, it can actually break off branches or set the tree on fire and you're underneath it. If you've ever gone camping, there's this term called widowmakers. Never put your tent under a tree with big branches, because if lightning hits that and breaks the branch off and it falls on your tent, it'll kill you. Don't use a computer or a phone, because lightning can hit the phone lines or the electrical lines. That's why we have surge protectors that can help. Most of you don't have landlines anymore. Telephones have actual cord into the wall. We use cell phones. But it used to be that if you, and it still does happen, if you are on a phone, a landline, and lightning hits the phone line, you can actually get a shock. My wife, years ago, was on a phone that basically exploded in her hand. If you're going to be outside, you can stand under trees. Just stand under shorter trees. And why is that? Because lightning's going to go for the taller tree first. And actually being in your car is relatively safe. Not because your tires are rubber, that's the myth, that your tires are rubber and so it's like wearing rubber shoes, rubber doesn't conduct. It's that if lightning does hit your car, the car itself is metal. The lightning will follow your car around you and not hit you. Alright, we've all passed the safety lecture, so now it's on to our next scary thing, tornadoes, in part 3.